This is the monkey and the hunter physics thought experiment. This is mostly a math-free version on this video. I'm just going to explain the concept. There's two different versions of this story. So the first version I'll show is the one I learned when I was in school many years ago, and it's a simpler version. And then after that, I'll show a little more complicated version. And I'm going to explain these very simply, so I think pretty much anybody could understand them. All right, the simple version right here is you have a gun pointing horizontal. There's a target right there that's level with the gun. This is a very old thought experiment that came from back in the days when more people were hunters. So the story goes is there's a hunter right here with a blowgun or a rifle. There's a monkey hanging from a branch. And right when that person fires the rifle or shoots the blowgun, right when that projectile comes out, the monkey drops from the branch and falls. The projectile falls, say the bullet, for example, falls, and the bullet will always hit the target. This version is a little easier to understand because I think anyone can imagine that if you have two objects that you're holding out and you drop both of them at the same time, they're both going to hit the ground at the same time and fall and be level with each other the entire time they're falling. So this bullet right here has a velocity in the x direction. It has no velocity in the y direction. And gravity will only affect velocity in the y direction, pull everything down. So if this bullet's traveling at 100 meters per second, for example, it'll always travel in that direction. Even if gravity's pulling it down that direction, no matter how fast it's going that way, it'll always travel at 100 meters per second that way. So when you drop your two objects at the same time right here, this bullet and that target are both falling identical, and they will always be level with each other, like my pin falling right here. And this bullet continues to head towards the target, so the bullet will hit the target. Here's the more complicated version that almost nobody would understand, save the physicists. If that gun is pointed up at the target, right when that bullet leaves the rifle and that target drops, that bullet will always hit the target, no matter the angle of that gun. So whether that gun is pointed up at 90 degrees or 0 or negative 90 degrees or anywhere in between, the bullet will always hit the target unless it's just a really long distance away and there's a lot of drag from air. So if you ignore air resistance, the bullet will always hit the target. What I understood is that I could imagine with some careful planning, you could have that bullet at just the right velocity, have that target at just the right distance, and then when you fire the gun, the bullet leaves the rifle, the target drops at the exact same time, then you can plan for it so that that bullet will hit the target. But how does this work so that the bullet will always hit the target no matter the distance of the target and no matter the velocity of the bullet? Physicists will explain this by saying that they are both falling. Even though that bullet is traveling up and rising in elevation, it is actually falling. And I thought, what kind of sorcery is that? Because that makes no sense. If you have a friend up on a balcony or a rooftop and you throw them a ball, you don't say, look at how that ball fell up to them. The ball is obviously rising, it's not falling. Or if you have a rocket shooting up into outer space, you don't stand back and look at that rocket flying up into outer space and say, look how that rocket is falling up. But it turns out that the bullet, even though it is traveling up, it is also falling down, and I'll show how that can happen. Okay, I'm going to show three analogies here. The first analogy are these two people floating on a barge that's floating down a current. The engines go out on the barge, so they're flowing obliquely or kind of sideways going down that current. This person on the down current end of the barge wants to run up to the other person at the other end of the barge. Then you can tell, obviously, no matter how fast this current is in this river as it flows down, and even if that current is accelerating and making them fall faster and faster in the downward direction, the person at this end of the barge is guaranteed to be able to run over to the person at that end of the barge. And so that's why when the bullet leaves the rifle here, even though gravity is accelerating everything that direction, the bullet is still guaranteed to hit the target. Another example is if you just get rid of the barge and say these are two people who had a ship that sunk. They're out in the middle of the ocean so they can see land nowhere around them, but there's a strong ocean current pulling them that direction. They don't know that they're being pulled in that direction. This person's floating in their life jacket here, and this person's floating in their life jacket here. So this person will swim over to that person right there. So from their perspective, this person is just swimming in a straight line to them. Now we can put a helicopter right here, and let's say that helicopter has GPS, so it can stay in that one point over the ocean. The people in that helicopter aren't going to see this person swimming in a straight line going that direction. They're going to see this person getting closer to that person, but both of these people are flowing in that direction with the ocean current. If this person right here is able to swim faster than the current, then they'll move up towards the top of the page. But if that current increases in velocity and starts accelerating like gravity, then eventually this person swimming up, their upward velocity is going to be outmatched by the downward velocity of gravity. So at first they'll have a slow downward velocity because that's the way gravity works. It accelerates. So initially the velocity downward is slow, but that velocity gets faster and faster. So at first this person is swimming up, his velocity is faster than the current, so he'll form an upward part of that parabola. But as that downward current gets faster and faster, he can't keep up with it, so he'll start going down as well. All right, so the first analogy was the barge. The second one was two people swimming in the ocean. The third analogy will be just two astronauts floating out in space. In space, there is no absolute movement or sitting still. So these are just two astronauts, and they have their jetpacks on. This person fires his jets to go over to that person. From their perspective, he is just going in a straight line. Now put a large planet over here with a lot of gravity. So even though this person is going in a straight line here, they're both being pulled down by gravity. And that planet right there causing the gravity could just be planet Earth. And so that's how everything falls, whether they're in outer space or whether they're in the atmosphere just above or just off the ground. He's going up, but they're both being pulled down to the planet. The next image will be a stop motion demonstration. And then I'll show how I did that afterwards with really simple math and just one equation. So you can watch that if you want. You can get an app for your phone. I think most of the video apps will have something where you can take pictures and do a stop motion animation thing. What I did here is just made out my little graph right here. I have a bar going across. I'll call it the gravity bar because it's how it drops and it tells you how fast everything's supposed to drop. Tape a target to one end of it. You can just use construction paper, or cardboard, or whatever. Put your bullet at the other end. I measured off 5 centimeter increments. So every time I took a picture, then I just moved the bullet up 5 centimeters. So the velocity of the bullet is 5 centimeters per frame. And then as for how fast everything drops right here, just use the formula 1/2 at squared equals distance. Acceleration can equal 1, so it just becomes 1/2 t squared equals distance. T is your time. Set up a table right here and just start plugging in numbers and make a little table. Time will equal 0, and then I did 0.5 increments. So 0.5, 1, 1.5, 2, 2.5. And then whatever your time equals, you plug that in right here and you'll get your distance. Each one of these right here is a frame. So the way this works is every frame, the bullet moves 5 centimeters. And so if your first frame will be 0, right here the distance that this thing falls is 0. And then at 0.5 seconds, then you move that bar down. You can't really move it down that far because that's a small distance. You get to 0.5 centimeters, then 1.1 centimeter. I should have written here, this is in centimeters right there. And then every time you take a picture, you move the bullet 5 centimeters up and you drop the whole stick down according to whatever it says right here for each frame. Since you're squaring your time right here, this will not be linear. So as this number for time gets bigger and bigger, you're going to get larger and larger gaps right here. So this bar is going to fall faster and faster with each frame. At first, that bullet velocity, 5 centimeters per frame, that bullet velocity will be faster than the rate it falls. And so that bullet will go up and you'll get the top part of your parabola or like a hump from the parabola. But as the seconds tick by, the upward velocity of the bullet can't keep up with the downward velocity from gravity, and the bullet will start to curve down like this as these gaps get wider and wider because everything drops faster and faster. Physics teachers do this in real life in their lab. They'll just have a piece of aluminum foil or something go over the barrel of the rifle. or the barrel of their air gun. So when the projectile comes out, it'll break that aluminum foil and it'll break a circuit. And that target is attached to an electromagnet. So as soon as the bullet comes out, it breaks the circuit, the target falls, and then the bullet will always hit the target. But if you wanted to, you could attach this target to a long, rigid bar right here and have this bar held up by an electromagnet on each end. And then when they fire that projectile right there, the whole bar will drop. So the bar will drop, the target will drop, and the bullet will drop, all at the same time and at the same rate. But you may get a vacuum effect though, where as this bar falls down, it could create a vacuum on top and the bullet could kind of stick to the bar. I don't know. Also, I don't know if anybody could come up with anything that's long enough and rigid enough that it wouldn't sag, so it may not work in real life, but it's just an interesting thought experiment at least. One last thing on this also, on my time increments, you can adjust your frame rate when you take a picture. So I used 0.5 seconds for each frame. So every time the bullet moved along, it sat there for a half a second before it moved again, and then that way that time rate or that frame rate matched right here. If you watch my stop motion thing, you'll notice I did it twice. The first time the bullet actually went twice as fast. So instead of using a half a second increments for my frame rate, I did 0.25 seconds or quarter second increments. So it didn't match right there. But it just made everything travel faster and kind of created a neat look, I think. Feel free to see the version of this where I delve more into the math and detail. The math was really simple, just high school or middle school stuff. The tricky part was putting all the equations together in the right order to make all of this work out. So it's kind of like an intricate jigsaw puzzle or something. So you can see that if you're interested.